All right, welcome back. We are going to dive into diagonalization next. So, first, we say a square matrix A is similar to B if there exists an invertible matrix P such that A equals P times B times P inverse. Now, A is diagonalizable if A is similar to a diagonal matrix D. So what does that look like? It means that A is equal to this invertible matrix P times a diagonal matrix times P inverse. And remember, a diagonal matrix means that everything is 0 that's not on the main diagonal. So the only non-zero thing is on the main diagonal. And yeah, that is what it means to be diagonalizable. Now, if this is true, does that mean we could just like move the P inverse and the D around and say A is equal to P times P inverse times D, and P times P inverse is just the identity, which means A equals D? No, because in general, matrix multiplication is not commutative. You can't just change the order of things. So we're going to see most of the examples of diagonalizable matrices are not already diagonal, such as example 3 here. Let's look at this. Here is a matrix A. It can be shown that if this is P, and here is a diagonal matrix D, then A is equal to P times D times P inverse. And P inverse is this thing here. Okay, so you could do it with a computer if you want, or if you feel like doing some extra matrix multiplication, sure, you could calculate P times D and then do that times P inverse and check that you get the same thing as A, but we don't have to. What we're going to do is we're going to calculate A squared and A cubed by hand, and we are going to see that it is tedious. And then after doing that, we're going to see how there's an easier way to do that using the diagonalizability of A. So first, let's calculate A squared. We can just use the row column rule or whatever your favorite method is. So that's what I got there. For A cubed, we can say that A cubed is A times A squared. So the numbers are getting a little bit bigger, but you can work it out with a calculator. And this is what you should get. All right, so that was pretty tedious. You can imagine that like calculating A to the power 100 or something really big, it's not as simple as just like raising the numbers to the power 100 in them, right? Because matrix multiplication involves, the row column rule or linear combinations or however you want to think about it. It's more complicated than that. So you can see why this is complicated for higher powers of A. But what if we have a diagonal matrix D? Is it easier to calculate powers of that? Well, D squared, for the 1, 1 position, we're going to have negative 1 times negative 1 plus 0 times 0. In row 2, column 1, we have 0 times negative 1 plus 2 times 0. That's all going to be 0. In row 1, column 2 here, we have negative 1 times 0 plus 0 times 2. In row 2, column 2, we have 0 squared plus 2 squared. So we end up with 1, 0, 0, 4, like so. So that was a little bit easier because we had all these zeros to multiply. And 0 is one of my favorite numbers to multiply by other numbers. Always a pleasure. Now let's do d times d squared to calculate d cubed. The same thing's going to happen when we're getting a result on the main diagonal. We're multiplying two non-zero things together. But as soon as we're looking at like a row 2 column 1 entry where the row and the column are different, all of the non-zeros are going to line up with a 0, like so. So we just get -1 and 8 on the main diagonal. And that is the same thing as -1 cubed and 2 cubed on the main diagonal. So my guess for a general formula is d to the power n is probably going to be -1 to the power n and 2 to the power n on the main diagonal and 0 everywhere else. Now that is much easier to calculate if n was like 100. If I wanted to do d to the power 100, it would just be -1 to the power 100, which is 1, and then 2 to the power 100, which is, well, maybe that is hard, but at least it's easy to write down like that. So that's much easier to do. Now, how can we find a formula for a to the power n in terms of p and d? Like, can we use d to calculate a to the power n? It turns out, yes, we can. There's a trick. So a to the power n, because a is equal to p times d times p inverse, that just means p times d times p inverse times itself n times. And what I see here is that p inverse times p is the identity. And all of the ones in the middle are going to cancel out. Like this last one here, this p inverse is going to cancel out with whatever the next p is. And this last p here would cancel out with the p inverse before it in the ... part. The ones on the outside do not cancel out, but we could write this as p d I d I, like so, and multiplying all of these diagonal matrices by the identity doesn't change them. So this just gives you p times d to the power n times p inverse, and that is a nicer formula for a to the power n. And that is much easier to calculate, even for a computer, when the matrix A is big, or when you want to calculate a big power of it, when the n is big as well. Okay, so let's just check that this formula here for diagonal matrices raised to powers works in general. So if this is any diagonal matrix here, you can write it like this, where again everything that's not on the main diagonal is all 0. Now, to see what happens when you have an entry that's not on the main diagonal, like row I, column j, where the I is not equal to j, like for example this looks like row 1 and column 2 here, the way you're going to calculate those are, well, most of the terms of this are going to be 0 times 0, because most of the entries here are 0, until you get to the point where you're at entry number I. When you get to entry I, we're going to have a non-zero entry in row I, and column j row I must be 0, because we're talking about something that's not on the main diagonal. So that's going to be 0. And then maybe there's going to be some other terms where everything's 0 until we get to term number j of this sum. In term number j, in the picture that's 2, well, entry number j from row I must be 0 because that's something that's not on the main diagonal. but then entry number j in column j is that jth diagonal entry. Well, that's also going to be 0, so everything here comes out to be 0. If you get something that is on the main diagonal, like if the I equals j, then this is a little simpler. Everything is going to be 0 times 0 until you get to the ith entry, where you get di from the row times di from the column, and then everything else is 0 times 0, and that just gives you di squared. So this tells you what every entry in D squared is for any diagonal matrix D. It's still going to be diagonal because everything that's not on the main diagonal came out to be 0, like this. Everything that is on the main diagonal just comes out to be that di squared. And so you get this diagonal matrix. And now when you do that times d again and again, the same principle is going to apply each time. So you can just see that d to the power n is going to be basically the way we thought it would work over here. Like so. So we're going to see that this formula that we worked out, that like if you raise a diagonalizable matrix to the power n by doing it in terms of its diagonalization parts, an invertible matrix times a diagonal matrix times its inverse times p inverse, then all the p and p inverses in the middle cancel out the same way we just showed, and we can state that in terms of coordinates. And that's what the next theorem's going to do. This is going to give us a nice way to think about how raising a matrix to powers works in terms of the grid made by a basis whose columns are the columns of this invertible matrix P. But we'll get to that in the next video.